All right, welcome back everybody to MTED110. Today we're going to be doing lecture 10B, which is the last lecture of the semester. It's been a long run, but a very, very fun one, I think. And I'm really, really excited about this particular lecture because, like I said in the last one, I've been trying to develop this number visualization code for a while now, and I was finally able to do it. So I'm excited to show you what some numbers look like to give you a more intuitive idea of what numbers look like. Okay, so let me go ahead and cut to the slides here. Let's see. Oh, there we go. That's right. We left off here last time. So today what we're going to do is we're going to be talking about number systems. So the one thing I want to point out first is that we're talking about number systems now as opposed to numeration systems, which are different. And we explored those in chapter 2. So let's get some definitions and make sense of these ideas. First, a set is just a collection of objects. So that's all it is. So anytime we talk about a set, we're talking about a collection of objects. Next, a number system is a set of numbers together with a set of operations on those numbers and the properties that the operations satisfy. And we're going to see some examples of that in just a minute. But basically, it's a set of numbers, and then you've got a collection of operations as well, like addition, subtraction, multiplication, division, and then the properties that those operations satisfy. So you have things like commutativity, associativity, and whatnot. Now, we say that a set of numbers is closed under an operation if, when operating on any two numbers in the set, the result is also in the set. So this is an important thing to consider. Basically, what we're saying is that if I take two numbers from that set and I operate on them in some way, will the result still be in the set, or will it jump out of the set? Like if I take, for example, if I take two positive numbers and I add them together, will I always get a positive number? Or will I possibly get a negative number? Because we could be considering the set of positive numbers, taking two elements from that set, operating on them, and seeing if we land in the set again. That's the idea. We're going to see some examples in a minute here. Before we get to the sets of numbers here, we need this definition, the multiplicative identity. So for any real number, or I should say, I'll just say this. The multiplicative identity for the set of real numbers is the number 1. And the reason is because for any number a, if you multiply 1 times a, you get a again. And if you multiply a times 1, you get a again. So 1 is what we call the multiplicative identity. Now, remember in the last lecture, we talked about the additive identity? The additive identity was 0, because whenever you added something to 0, you got that thing back again, right? Well, 1 is the same thing except for multiplication, because if I do 2 times 1, I get 2. So we call it the multiplicative identity. All right. If the product of two numbers is 1, then each number is called the multiplicative inverse of the other. So, and if a is not equal to 0, then we write its inverse, multiplicative inverse, as this or this usually. So just like in the last lecture, we were talking about additive inverses, right? We were saying, oh, if you take 2 and you add it to its inverse, you get 0. So we're talking about the same concept here, except for multiplication. And what we're saying is if the product of two numbers is 1, then they must be multiplicative inverses, or sometimes we call them reciprocals. So let's see some examples here. 3 and 1/3 are multiplicative inverses, because when I multiply them together, I get 1. Why do I get 1? Well, now we know, right? Because it's like 1/3 3 times would give you a whole, and that'll give us 1. Or here, -5 and -1/5, those are multiplicative inverses, and so on and so on. Here, 2/3 and 3/2, those are multiplicative inverses because you get 1. And then you can do this for basically any number except for 0. Any number except for 0, because you can't divide by 0, right? But even like pi, 1 over pi, that's its multiplicative inverse. And in general, a times a to the -1 is a times 1 over a, which is 1. So that's what a multiplicative inverse is. All right. Now, this is a picture of the set of real numbers, and it's really difficult to find a proper picture of what this looks like. There are a lot of them online. There's a lot of, like, if you Google sets of numbers or the set of real numbers, there are a lot of pictures that try to make this clear, but they're not pictorially accurate because the pictures give the impression that there's numbers in a place where there aren't. It's kind of hard to explain. But anyway, so this is the best one I found, and I actually had to tweak it to make it a little clearer because I didn't really like the way that they had labeled some things, so I relabeled them myself. But the idea is this. We've got a whole bunch of sets of numbers, and a lot of them are nested inside of one another. And what we're going to do right now is we're just going to explore the differences between these sets. So let's go all the way back to the set of natural numbers right here. Okay, so the natural numbers are all the counting numbers, 1, 2, 3, 4, the positive whole numbers. Now I'm going to go ahead and lump 0 in with the natural numbers, partially because it makes the picture a little easier, because I don't want to have an entire other set just to talk about the natural numbers and then also the number 0, right? So we're just going to throw 0 into the natural numbers, and we're just going to say that it's a natural number for our purposes here. Now, that set, all of the positive whole numbers, is contained inside the set of integers. And the set of integers is right here. Actually, let me make this a little bit smaller. Do this. So the set of integers is everything inside of this blue oval right here. And remember, the integers are all of the positive and negative whole numbers. So you can kind of view this picture like so. Let's see, let me do this. In here, this is like all of the positive and, the positive whole numbers. And then this little band out here, the blue band, these would be all the negatives, right? But what you can see is that when you take this little blue band and combine it with the pink oval on the inside, you get all of the integers. So that's what this picture is showing you. It's showing you that the natural numbers are contained inside the set of integers. So it's like natural numbers, integers like this. So the integers have more numbers in them, so to speak. Okay, and then moving on out, let's look at the next one here. Maybe I'll use green. We've got the rational numbers. So the rational numbers are anytime you can write a number as a ratio of two integers, right? We had talked about that before. As long as the denominator is not 0. Remember, we're still excluding division by 0 at all costs. So here, the rationals are just any number that can be written as a ratio of two integers. So first of all, notice that the integers are actually in that set, right? And that's because you can write things like, I could write the number 2 as 8 divided by 4. Now, 8 divided by 4 is a rational number by definition. We actually saw that in a previous lecture. 8 divided by 4 is a rational number, but 8 divided by 4 is equal to 2, and that's an integer. And it's a natural number, actually. So again, you get this nice containment, right? Containment of these numbers. And every time you allow more numbers in, the oval gets a little bit bigger. So the rational numbers include lots of stuff, right? 1/2, negative fractions, any like these decimal representations. Remember, we were saying that a rational number always has a decimal representation that terminates or it repeats infinitely, right? That's what a rational number is. So those are included in there. Okay. Now, one of the reasons I like this particular picture that you can find online is because it takes the time to distinguish between these next two sets of numbers. All right, so let me erase some things here. Let's take a look at this next larger set. Now, this set, maybe I'll use red in this case. So this set here in this oval, oop, lost it. This set right here in this oval right here, these are called the algebraic numbers. And the algebraic numbers are particularly nice because they can be, how do I want to say it in a meaningful way? The algebraic numbers are numbers that can fit inside of a polynomial in a nice way. So basically, you're an algebraic number if you're the root of a polynomial that has rational coefficients. So let me try to explain what that means. Let's take for example square root of 2. Now square root of 2 is algebraic because if I consider the function f of x equals x squared, and I plug in the square root of 2, then what I get is 2 back, right? So f of square root of 2 equals 2. Sorry, let me write it like this. Squared. equals 2. So what that means is that we can actually find a polynomial where we can make that result the 0. We can make root 2 the 0 of that polynomial. So let's try this one. Let's try p of x equals, we'll say x squared minus 2. Here we go. And we'll use square root of 2 again. If I plug in the square root of 2 to this polynomial, then I get 0 because I'm going to get 2 minus 2, which is 0. So that's the idea. You're an algebraic number if you can do that. And the coefficients of all of these powers right here, like whether it's x squared, x cubed, x to the fourth, x to the 1 billionth, those coefficients have to be rational. Now, the reason that it's important to distinguish between those two is because if you look here on this picture, let me use, I don't know, purple. This band right here that I'm highlighting in purple, trying to get like all this stuff out here, right? All this stuff. Yeah, so this band that's in purple, these are all irrational numbers. So the irrational numbers, remember, they have a, for example, they have a non-repeating infinite decimal representation for one, and they can't be written as a ratio of two integers. So what's interesting here is that a number like square root of 2 can be essentially like like a zeroed out by rational operations. That's a very hand wavy, vague way of explaining it. You don't have to like have this memorized per se, but it's good to know that it's actually there. Now, the other reason I like this picture is because the irrational numbers are as they should be, and they're basically this outer band. Everything outside of these, outside of the rationals, everything here, those are irrational numbers. So you've got algebraic irrational numbers, and then you have these other numbers, these really, really fancy numbers that are called transcendental. So transcendental numbers are numbers where this is not possible. So basically, you can't find a polynomial that has rational coefficients that will make that number a 0 of that polynomial. So these numbers are particularly fancy. They're particularly important. They're called transcendental. Anyway, so this picture is nice because it distinguishes between transcendental and algebraic, and it also shows you that these are all the irrational numbers. The other thing I wanted to point out is notice that the algebraic numbers include all of the rationals, integers, and natural numbers because we can always find a polynomial like that if you've got something as nice as a rational number or an integer. So these funky looking numbers here, those are a little more intriguing actually. Okay, so this is kind of it. And so once you take all of these numbers, the entire set itself, clear some things here, clear, clear, there we go. So this entire set, I'll just do it in black actually, boom. Oh, actually, sorry, the entire set right here, that's the set of real numbers. That's the set of real numbers. So the real numbers is like if you were to take all of the irrational numbers and all of the rational numbers and put them in a bowl together. And in that bowl, you've got other things. You've got transcendental numbers, algebraic, but they can all be classified as rational or irrational. See? Rational or irrational. So every real number is one of these types. And that's an important thing to keep in mind. Every real number is rational or irrational. And we're going to see something very pretty in a few minutes here. Okay, but let's ask ourselves this. Let's ask ourselves some questions about closure. Because remember, we were talking about closure, and we were saying that, let me go back here. This right here. A set is closed if when I take two numbers and operate on them, the result is still in the set. So let's take a look at some of these sets and consider closure under certain operations. So let's try, for example, okay, let's do natural numbers first. Now, is the natural numbers closed under addition? That's the question. So what are we asking? What does it mean for the rational numbers to be closed under addition? Think about it. Okay, and now talk out loud about what you're thinking about. Say something out loud to yourself or to your dog or whatever. What does that mean? What are you thinking? All right, now let's explore it together. if a set is closed under addition, that means if I take two numbers in that set and add them together, I'll get another number in that set. So if I take any natural number, any counting number, 1, 2, 3, 4, 5, right, and I add them together, do I end up as a natural number? Or do I suddenly become negative? Or do I become like a rational number? Or am I like an irrational number? And you'll see that that's never going to happen, right? So yes, the natural numbers are closed under addition. What about subtraction? If I take any two natural numbers and subtract them, will I still remain in the natural numbers? In this case, we won't. Here's a counterexample. Let's do, here we go, 2 minus 9. That's -7. -7, there you go, that's -7. -7 is not a natural number, so it's not closed under subtraction. And then what about multiplication? If I take any two positive whole numbers and multiply them, am I guaranteed to get another positive whole number? What do you think? Think about it for a moment. Yeah, yeah, you will. You will still be inside the natural numbers. So it is closed under multiplication. What about division? If I take any two natural numbers and divide them, am I guaranteed to get a natural number back? Think about it. In this case, no, that's not going to work, right? Because I can think of almost any two natural numbers, right? Not any, but almost any, right? Here, 2 divided by 3. That's not a natural number. That's a rational number, right? And that's a bigger set. The rational numbers have more numbers in them in some sense, right? Because you've got all the integers and you've got all the fractions. But we're not talking about the rationals. We're talking about the natural numbers, which is that little fancy letter N right there. Okay, so there's those results right there. Now let's do the next one. What about the set of integers? Integers. And yeah, think about that for a minute. Is the set of integers closed under, let's say, addition? Is it closed under addition? Yeah, it's definitely closed under addition. And it turns out that it's closed under almost all of these, right? Except for division. It's not closed under division because I can divide two integers and end up as a rational number that's not an integer. So that's the idea. Now, think about number 3. 3, we're looking at the rational numbers. So any number that can be written as a ratio of two integers. Is it closed under addition? Think about it. Now this one I want you to talk out loud for a moment too. Kind of say out loud what that means. Maybe say some examples of some numbers if you add them together. All right, now let's talk about it together. In this case, it's going to be closed under just about every single one of those, although technically not division. So here, let's make sense of this here. If I take two fractions and add them together, do I get another fraction? Or in this case, rational number? The answer is yes, I'll definitely get another one. If I subtract two of them, I'll also get one. If I multiply two of them, I'll also get one. But if I divide, I can't say it's true for division because there's one number that messes everything up, and that number is 0. So I can't do this. So in this case, the irrational numbers are not closed under division. They're not closed under division, so they're closed under everything else. However, if I take everything but 0, then it is closed. So in some senses, we'll talk about the rational numbers and we'll talk about their closure, but as long as you don't include 0 when you divide. But anyway, and then lastly, there's this one, 4, the set of real numbers. Now that's the biggest set. That's the biggest set, excluding complex numbers. We're not going to talk about complex numbers in this class, but it's basically, the complex numbers would include all the reals. So if I were to go back to this picture, the complex numbers would be would be like out here, and then that wouldn't be there. These would be the imaginary numbers, and then these would be the complex numbers, which we denote with a fancy C. But we're not going to worry about that here. Students will learn about that later on in high school. Okay, yeah, so the real numbers are closed under all of them, again, except for possibly division. So oftentimes we don't like to talk about closure under division. We'd rather rephrase it in some way where we can avoid dividing by zero. Okay, so I guess what I would say here is the real numbers are closed as long as you exclude zero under division. All right, so one thing you might have noticed is that all of these previous number systems, those are finite. So a number system, for example, would be the naturals under addition. That's a number system right there. But these are all infinite. There's infinitely many naturals, infinitely many fractions, infinitely many whole numbers, right? There's infinitely many. But there are some number systems that are finite, and those ones are equally important. And in fact, you've been using them for your whole life. Um, so here's an example of one, and this is a very important number system, and it's called modular arithmetic, or sometimes it's called clock arithmetic. And the easiest way to explain this is that this is the system that you use whenever you want to determine if it's AM or PM, or like what time it is AM, PM. Let's try an example. For those of you who know 24-hour time, what is 7 plus 8 in 24-hour time? Well, that's going to be what? 7 plus 8 is 16. Or what is it? 15, right? So it's 15. So that'd be 1,500 hours in 24-hour time, right? Some of you might be familiar with this. Right, and what's midnight? Midnight is 0 hours, and then 1 a.m. is 100, and 100 hours, and then 9 a.m. is 900 hours, and so on. So 7 plus 8 in 24-hour time is 1,500 hours. But what's 7 plus 8 in 12-hour time? Well, in 12-hour time, it's going to be 3 p.m. 3 p.m., right? Why is that? Well, you basically said, okay, you're going to get 15, but then you have to mod out by 12 and just look at the remainder. So if I subtract 12, then I get 3 p.m. That's the idea. So that's modular arithmetic or clock arithmetic, and you can try it yourself. What's 1,600 hours in 12-hour time? We would say 1,600 hours is 4 p.m., right? There we go. So that's a way of doing modular arithmetic. So you've been doing it your whole life pretty much. But what's really cool is that this thing comes up all over the place. It pops up everywhere. Uh, this is one of my favorite examples because once students get this, it simplifies things so quickly. Um, let's look at this. Do you remember having to simplify radicals that looked like this, these nasty looking things? And they would get pretty gnarly, right? And there'd be like fractions and stuff, and maybe this number at the front would be like, or not a 2, but like a 10 or something like that. Well, you can use modular arithmetic to simplify this rather quickly, because what this is saying is cancel out a bunch of squares. And that process is kind of like what we were doing right here. It's kind of like canceling things out, right? Because what's division? It's repeated subtraction. It's repeated subtraction. So let's check this out. Here, this is going to end up being 2 because you get the square root of 4, right? In fact, let me write this out like so. Square root of 4, square root of x to the 5th, square root of y to the 4th, square root of z to the 7th. And again, you don't have to be able to do this. This is just about knowledge on the mathematical horizon, okay? But check this out. So square root of 4 is 2, and then this is what you had to learn how to simplify back in algebra. And the way that you can do it is you ask how many squares are in there, right? Because for each square of x you have, you can pull out an x. And so you end up getting, what is that? X, 2x's. And then here you'll have y squared. And then here you'll have z cubed. And then you're going to have some stuff left over. You're going to have x to the 1, y to the 0, which we don't need, and then z to the 1. And what these things are the remainders. These are the remainders, exactly like what we did back here. Oops, right here. It's the remainder that gets left underneath because you don't have a whole square to take out. So that's what's going on right here. Again, I can explain that more in the collaboration meetings if you want to see, but this is something that your students will use when they get into high school. So if we talk about it earlier on, they'll be well prepared to do that, and they'll be able to understand that algorithm. Okay. All right, so now we're going to come to my favorite part here. So I've been preparing this for quite a while. Uh, and this is where it comes down to. What we want to do is I want to give you all a proper visualization of the difference between a rational number and an irrational number. So we know what the difference is between them, but what we're going to do is we're going to leverage our basimal numeration system to get a unique look at these numbers. So the first thing you got to remember is that a rational number either has a terminating decimal representation or it has a repeating non-terminating decimal representation, right? It's going to go chick, 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 chick in some period where it's basically a whole bunch of repeats of that period. That's a rational number. In contrast, an irrational number doesn't do that at all. An irrational number goes on forever, its representation does, but it never repeats. There's no like, repeating block that occurs at some point. So here's what we're going to do. We're going to set it up like this. First, we're going to list the decimal representation of a number to like, 100,000 digits. So for example, pi, except imagine this went on for 100,000 digits, okay? 100,000 digits of pi. Then what we're going to do is this. We're going to take each digit and we're going to assign a color to it based on which digit it is, 0 through 9. So for example, everywhere I see a 0, I would put a red. So like, that would be red. Oop, let me make that a little smaller. Here we go. So that would be red. That's the only 0 here. 1 would be an orange color, right? So let me pick the color orange here. So that would be orange, orange, orange. 2 would be yellow, 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 yellow. Second here, let me scoot that over. Yellow, yellow, yellow. Okay, 3 would be green. We'll do this light green here. So 3, 3, 3. And you can kind of get the idea, right? 3, 3, 3. Go through and do this for all of the digits. Okay, 4, 4, 4. Just going through, and it's like I'm painting every digit with a color based on the digit. 5 is that bluish color, so maybe I'll use this for 5. 6 is a little bit darker blue. 7 is a darker blue. Then 8 is going to be like a purple. Okay. And then 9 is going to be this like lighter color purple. So let me pick this one here. Anyway, I'm just trying to give you an example of how this little mapping would actually work. So this is essentially what it's doing. I hope that makes sense. Mapping a color to each digit based on the digit. And now what we're going to do is we're just going to print out 100,000 digits or actually a million digits, and we're just going to see what it looks like. So what we're going to do next is we're going to assign each one of these digit color combos to a single pixel in an array. See what I've got here? Yeah, in an array. And then we're going to take a look at what it looks like. So the first number I want to look at with y'all is 1/7. And 1/7 is this decimal representation here. And that's the repeating block. So it has a period of 6, and it just goes 1428557, 1428557, 1428557. And we saw that, right? We saw that back in chapter 6 or chapter 7, one of the two. Anyway, but let's see a picture of what that looks like. There it is. Zoom in here so we can keep this in mind. So what you can see over here, what you can see over here is a picture of the number 1/7. Now watch this when I zoom in. And I'm going to go up to this corner up here, trying to get as close as I can to the upper right-hand corner. Oh, sorry. Got ahead of myself. Come back. Thumbnails. There we go. Hide this for a second. Yeah, so it's right up there. Yeah. And you notice that it's basically just a repeating pattern. It's orange, green, yellow, purple, blue, blue, orange, green, yellow, purple, blue, blue, orange, green, yellow. Those are the digits right here. It's these things right here. 1, 4, 2, 8, 5, 7. So, right? So it's orange, green, yellow, purple, light blue, dark blue. That's what it is. And this is a picture of what it looks like. Notice that it's just a nicely repeating bunch of strips, right? It's just a bunch of really straight, cool lines. And so that's what that number looks like visually. I hope you can appreciate what that looks like, right? That's the number 1/7. Nice picture of it. There you go. Pretty cool, huh? Okay, what's the next number I wanted to look at? Let's see. Now let's look at 1/3. Now notice 1/3 is just it's just zero point 0.3 repeating, right? So 1/3, what's that going to look like, you think? Actually, yeah, let me ask you, what do you think it's going to look like? 1/3 repeating. Hmm, think about it. Well, let's have a look. It's going to be all one color, right? It's going to be all one color because it's just 3. It's just the number 3 over and over and over and over again, and 3 is green. So this is just a big green block. Let me go ahead and yeah, there it is, the upper corner. It's just a green block because every number in the decimal expansion is 3. Okay, now let's look at the number 1/8, which is 0.125. This is a rational number that terminates, right? So what does this one look like? Where are you? 1/8. Maybe, did I not include it here? No, I thought I had. 1 second. Where is it? 1/8. I must have missed it. Bummer. Oh, wait, I have it back here. Hold on 1 second. Do, 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 do. Hold on 1 second. I want to see if I can open this and let you see 1/8 because it's kind of cute. Come here, 1/8. Open. All right, 1/8. Can you see it yet? Not quite. Let me change my window. Give me one moment here. Where are you? Pick with, okay, okay. Oh yeah, okay, there we go. Hold on 1 second here. Just do this momentarily here so we can see it. Here's 1/8. Now, now what's funny is you might notice that like up there in the corner, there's like it looks like there's a little bit of like color right there. Let's zoom in, right? Let's zoom in on this. And there it is. There's the number 1/8 because it's literally just 3 digits and then zeros the rest of the way. 0, 0, 0, 0, 0, 0. So that's what it looks like. It's 1, 2, 5, 0, 0, 0, 0. And there it is. There's the orange, yellow, and blue 1, 2, 5. So that's what 1/8 looks like. Isn't that cute? Okay. Now let's go back to that other window really quick so we can see some other ones. Oh, now it's hiding from me. Give me 1 second here. There we go. Okay, come back here. There we go. Okay, so that's 1/3. What's the next one I want to take a look at? Oh yeah, how about this one? How about the number 111/117? So that one is 0.948717 repeating. Let's see what that one looks like. I'm curious. Here it is. This is 111/117. But sorry. Let's zoom in a bit. There you go. There's that same that same pattern, right? Just a bunch of vertical lines. All right, so that's kind of cute. That's interesting. Um, what about a number like this? What about a number that has a period of 53? So let me zoom in here. Actually, let me do this really quick so we can take a look at this number. Here, let me transition for a moment. How about this number right here? This number right here. So this number is a rational number. It's got a repeating decimal representation, but the period is 53 digits. It takes 53 digits before it starts to repeat. And that's what it looks, or we're going to see what it looks like right now. You ready? Let's take a look. See if I can pull it up here. Which one am I doing here? Oh, 576. Here we go. Let's look at 100,000 digits of that number. Here we go. Boom, there it is. So this is what that number looks like. And if I zoom in again, you can see that, oh, you can see that it's just this nice repeating pattern, right? You've got the same thing, except now the pattern is really long. The pattern is 63 digits or 53 digits long. So this is what 100,000 digits of it looks like right there. That's 100,000 digits of 576 over 107. How about we do a million digits? Oops, not that way. No, there we go. There's a million digits of it. So that's what it looks like if you had a million digits and you followed that pattern. Let me zoom in. There you go. So that's what it is. That's what that number looks like. Isn't that wild? It's just so wild. Okay, let's and there it is if I zoom out really far. Okay, so let's look at some other ones here. Let me go back to the slides. Let's check out this number. So this number is 365 over 4,789, and its period is 228 digits. 228 digits. So let's take a look at what that one looks like. Da, da. Which number is this? 365. Here we go. All right. Boom. That's what it looks like. That's what it looks like. So that's the number 365 over 4,789, just like that. Pretty cool, huh? And then again, if you zoom in, you can see that there's a repeating pattern because it's a rational number. Anyway, pretty cool stuff. I've got one last one to show you here. Let me transition back here. Let me show you this one. This one has a period of 6,456 digits. So let's go to that one. Where is it? Nope, is that it? Nope, that's not it. Okay. Okay. So check, yeah, okay. Now, so check this one out. The period is really, really long. So what you're going to notice is that it looks a little bit different. Let's check it out. Hmm. You see that? It looks so much more chaotic, but there's still a pattern there. You can kind of see almost like some like diagonal swooping going on, right? Some like patches of green and some little like spots of blue in the same pattern over and over again. That's because it's a rational number, right? That's a rational number. Let's look at it with a million digits. Oh, sorry, wrong one. Here we go. That's a million digits of it. And again, you can kind of see this repeating pattern. And the pattern is easier to see when you zoom out farther, or in other words, when you look at more digits on the whole. Let's zoom in again just for fun. There it is, just a bunch of little digits. And that's what it looks like. Pretty cool, huh? So that's a rational number. That's a rational number there. Now, let's compare this to some irrational numbers. And let's see the difference between a rational number and an irrational number. So let's look at the first one. Let's look at pi. Everybody's favorite irrational number, pi, right? Let's see what it looks like. Here we go. There's pi. There's 100,000 digits of pi. Do you see any patterns? Let's look at a million. Oh, wrong one. Here's a million digits of pi. That's what a million digits of pi looks like. Do you see any patterns? Zoom in. Oh, sorry. There we go. Zoom in. Any patterns at all? No. You don't see any patterns because it's an irrational number. This is what irrational numbers look like. This is what irrational numbers look like. They look almost like just chaos, right? Almost totally random. There's no repeating anything, right? So let's look at a couple others. Let's look at, let's see, what's another good one here? What do I have here? How about square root of 2? Square root of 2 is essentially the first irrational number ever discovered. What does a square root of 2 look like? Let's see a million digits of it. You ready? Boom. There it is. That's the square root of 2. See any patterns? You might see some little like clusters of patterns, but then once you zoom out, you realize that the pattern doesn't repeat anymore because it's an irrational number. So that's the square root of 2 right there. What's the next one? Let's see. Da, da, da. Square root of 3. Let's just compare it to square root of 3. Here we go. Let's do 1 second. There we go. Let's do 100K digits first. So there's 100,000 digits of the square root of 3. And here's 1,000,000 digits of the square root of 3. That's what it looks like. It's an irrational number. Okay, now I'll just do the last couple here. Let's look at e, which is the exponential base, the natural exponential base. You know that number e that you learn about in high school? And then we're going to look at this number phi, which is the infamous golden ratio, the golden ratio. That's an algebraic number, by the way, the golden ratio. It's actually in the picture from a previous slide. But let's take a look at it, right? So let's see what e looks like, and let's see what the golden ratio looks like. Let's see, what do we got here? There's the square root of 3. Oh, let me go back a bit. Let's do e. There's 100,000 digits of e. Ah, and there's 1,000,000 digits of e. So there's an irrational number, and there's a rational number. Actually, I got more digits. There you go. Rational, irrational. Rational, irrational. Isn't that amazing? I just think that's so beautiful. There's 100,000 digits. And here's phi. Here's what phi looks like, the golden ratio. That's what it looks like, 1,000,000 digits of it with this color pattern here. And that's it. So yeah, that's one of the reasons I love this. So that is what the difference between rational and irrational numbers is. And now you can like literally visibly see it. And the way that I constructed this picture is just using the decimal representation of those numbers. And just understanding how that representation works gives us this very beautiful interpretation of what these numbers are. Anyway, I just think it's absolutely amazing. So I was really, really excited to share that with you. Oh, incidentally, if you want to see any other number you could imagine, let me know in the collaboration meeting because I have a code to generate these and it only takes about a minute. It just depends on how complicated the number is. It only takes a minute to generate a new one. So if there's a certain number that you want to see, let me know and I'll generate it in the collaboration meeting for you right then and there. All right? Okay, so now what's interesting is this. There's one last cool thing about these rationals and irrationals, and we need this definition. We say that a set of numbers is dense if for every possible choice of two numbers in the set, there is always another number from the set that lies in between them. So let's see if we can make sense of that. Let's say I've got a line, like a number line, let's say. And I've got some numbers on it. Maybe this is 2, maybe this is 3. We say that a set is dense if no matter which two numbers I pick, I can find another number in between them that is also in the set. Does that make sense? Think about that for a minute. Think about that definition and see if it makes sense to you. Okay, now let's talk about it some more. We've actually already seen that the set of rational numbers is dense. That was one of the questions. I know it was on the homework. I think it was on an activity, and I think it was on an assessment too. Basically, if you give me any two rational numbers, I can always find a bunch of numbers in between them. How about here? How about this? How about you give me the numbers 1/2 and 3/4? Can I find a number in between those? Sure, I can. And I'm going to be clever about it here. I'm going to say, oh, this is 2/4 and this is 3/4. Well, a number that's in between those is 3.5 fourths. Yeah, that's a number in between them for sure. Absolutely for sure. And you could reduce that, or not reduce it, but you could write it as just a ratio of integers. If you split up 3.5 as like 7/2, and then you would get 7/16. And 7/16 is between 1/2 and 3/4. Um, and I'm sorry, I think I did the calculation wrong. What is that? Is that 7 divided by 2? 7 divided by 2? Oh, 8, sorry, 7. Wait, hold on. Now I'm like tripping myself out. Hold on. Oh, what am I doing? What am I doing? Not 3, not 3. 2. 2.5. 2.5 is between 2 and 3. So what is that? That's 5/8, and that's definitely true. 1/2 is less than 5/8 is less than 3/4, certainly. But you can just keep repeating this process. You could find one that's between 2 and 2.5, and then one that's between those, and one that's between those, and over again. That's what it means to be dense. That's what we say when a set is dense. The irrational numbers are also dense because if you give any irrational number, you can find another one in between it. Now, in contrast, the set of integers is not dense. It's not dense, right? So let's think about that. The integers are like these numbers, -1, 0, oops, 1, 2, 3, dot, 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 dot. Okay, so I'm going to give you the numbers 1 and 2. Can you find an integer that's in between 1 and 2? An integer that's in between 1 and 2? No, can't, right? You can't because the next integer after 1 is 2. So that's why this is not dense. The integers are not a dense set. But the rationals are dense, and the irrationals are dense. And one of the reasons that I really wanted to show you this picture is because of this. The definition of density is equivalent to saying this. Any real number can be approximated arbitrarily closely by rational numbers. So what that means is that we use those rational numbers to get as close to an irrational number as we would ever want. So in other words, we use those nice patterned pictures to get close to those chaotic pictures. And in fact, the rational numbers are so dense that no matter what irrational number you give me, I can always find a rational number that's as close to that as you want. So let me throw up these pictures again for a moment here. What I'm trying to say is this. I'm trying to say if you wanted to get close to a number that looks like this chaos here, then we can get as close as we want by using numbers that look like this. Yeah, that's what it means. So we build our world off of these numbers, these rational numbers. And this is something that I mentioned in my TED Talk. This is what I mean. These are the numbers that we use to compute anything, essentially, to build anything. Any scientific advancement that you physically hold is basically based off of these numbers. And the trippy part is that the rational numbers, even though there's a bunch of them, they actually don't make up very much of the real line. And that's more advanced mathematical theory. So if you want to study that idea, then you've got to study some more math after high school and probably after a bachelor's degree in it. But the numbers that make up the bulk of the real line are numbers that look like this. So yeah, the numbers that look like this, the irrational numbers, they are the ones that make up the bulk of the real line. And there's so many more of them that the rational numbers almost might as well not even exist. So like I can't even give you a good idea of the size difference, but how about this? Think about this. Numbers that look like this. Take the entire set of, wait, let me go back. Here we go. So numbers that have these nice patterns, okay? Numbers that look like this. If you take all of the numbers that have patterns like this and said that that was about the size of an atom, right? Like a tiny atom, then the size of the irrational numbers, the ones that look like this, is like the size of the universe. That's the comparison in size. Anyway, I could go on about that for a long time, so I'll stop here. Let me go back here. We're just about done. Um, all right, yeah, that's it. All right, that's it. So let's take a look at activity 10B really quick. Okay, activity 10B. Here you go. So there's some questions about closure in the beginning here. Is the set of rational numbers closed under addition, subtraction, multiplication? If not, give a brief explanation as to why. And some other sets about asking about closure. This is a really interesting one. This is a fun one to think about too. And then explain why the set of whole numbers is not dense. So that's pretty much it. That's it for activity 10B. Not too bad, right? Let's see. What else have I got here? Let's go back to my slides. One last thing, one last slide here, and it's just this. I just wanted to say congratulations, everybody. You made it through MTED 110. It's been a really, really fun journey. I hope you really enjoyed it. And I want to leave you with this last quote from one of my favorite mathematicians, George Cantor. He says, "The essence of mathematics lies entirely in its freedom." And I hope that maybe you can appreciate that quote now after having been through the course, because mathematics is very freeing. It's about freedom, and it's about describing our existence and our reality. And that's why I love teaching it, and that's why I love doing it. And your students will love it as well if you present it to them in a loving way and help them cope with the anxiety that comes with studying something as difficult as being able to describe your own existence and your own reality. Okay, so I think I will go ahead and stop there, and I guess I'm going to have to sign off now. Thanks again, everyone. I'll see you in the collaboration meetings, and as always, please ask me any questions you would like. All right? All right, have a good one.